All right, I think what would be most beneficial in our last 15 minutes would be to summarize everything we've been doing. What's been the point of it all? The textbook, being a differential equations textbook, emphasizes what you need to know to get the general solutions as fast as possible. Okay? Eigenvalues, eigenvectors get you the general solutions as fast as possible, help you solve initial value problems as fast as possible. That's their goal. But being a differential equations with linear algebra course, we also want to relate it to linear algebra, and that's why we talk about diagonalization, matrix exponentials, and discrete dynamical systems too. There is a relationship. I really emphasize discrete stuff in class as much as I do in the lectures. So let's just try to think about the big ideas here. Big ideas about what we've been doing. So this is, in a sense, a start on reviewing for exam 4 here, okay? Next Monday after Thanksgiving, we will review other stuff. This is a start in 15 minutes. You got a differential equation, a linear system. When I talk about this kind of stuff in the abstract, Y could be an n-dimensional vector in Rn, and A, therefore, would be an n by n matrix. When we do hand calculations, 95% of the time, n is 2. 5% of the time we did n is 3. Pretty much the rest of the time we never did any other examples when n is bigger than 3, at least as far as differential equations go. We did some higher dimensional things with pure linear algebra. But I want to talk abstract here. So Y is really a vector in Rn, though it's a time-dependent vector. It's a function of t. And A is n by n. So there is a generic linear system. What's the emphasis in the textbook? The emphasis is trying to solve it, find a general solution. First step, find the eigenvalues by solving the characteristic polynomial, find the roots. Solve the determinant of a minus lambda I equals 0 for lambda. In the case where n is 2, that's quadratic. You can always just use the quadratic formula if you have to. Once n is 3 or larger, it gets much, much harder. To solve for lambda, you have to have special situations where lambda is not too complicated. Technically, when n is 3, you've got a cubic. There actually is an analog of the quadratic formula for cubics, but it's not very pleasant. When n is 4, quartic, technically there is an analog for the quadratic formula for quartics, but it's really, really, really unpleasant. When n is 5 or above, it's actually impossible. People have proved it's impossible in general to solve for lambda exactly. Special cases you can, but in general you can't. You'd have to approximate lambda. We don't really worry about it too much, though you should still understand the big idea. Once you got the eigenvalues, you find the eigenvectors. What typically happens, you may want to write this down, I will not. What typically happens is, even when it's n-dimensional, where n is an arbitrary positive integer, typically you get n, well, maybe use of the word typical is not. Okay, say all the eigenvalues are real. If all the eigenvalues are real, typically they will be distinct. Distinct real numbers, if you assume they are all real. You'll have n distinct roots. And in that case, there's theorems, linear algebra theorems, that guarantee the eigenvectors will all be linearly independent and therefore be a basis for Rn. In that nicest of cases, if there are n real e-values. If there are n real e-values, say lambda 1 through lambda n, then there will be n linearly independent e-vectors. That's a theorem. When you have n real eigenvalues that are distinct, I forgot the word distinct, n distinct, that's important to emphasize, real eigenvalues, then there will be n linearly independent eigenvectors, and your general solution will be y equals k1 e to the lambda 1 t times the corresponding eigenvector v1 plus etc. Every term will be of that form. If all those lambdas are negative, then the origin for this n-dimensional system will be some sort of higher dimensional sink, real sink. If all those lambdas are positive, then the origin will be some sort of higher dimensional source. If at least one eigenvalue is negative and one's positive, then it's some sort of higher dimensional saddle point. It's hard to visualize, except when it has 2 or 3. What if the eigenvalues are not distinct, but say still real? That's where you have to bring in Jordan canonical form, technically speaking, though we only did that in the case where n is 2. It's not the approach the book takes, but it's the approach I took and the approach I want you to take, be able to handle on the exam. You'll see in last year's exam, it comes up on the take-home exam, the Jordan canonical form stuff. What if the eigenvalues are complex? Or maybe even a mixture of real and complex? Then it gets harder. In the easiest case, when n is 2, if you have one complex eigenvalue, the other eigenvalue will be complex as well. We're still after real solutions. We take that one of those complex eigenvalues, I'm not going to write it down, find the corresponding complex eigenvector. Bring back memories here. Write down a complex solution, use Euler's identity to separate that into real and imaginary parts. And almost as if by magic, the real and imaginary parts end up being linearly independent solutions of the original real system. Is it magical? It seems magical, but it's actually fairly easy to verify it, and the book does it in the 2x2 case. You do get cosines and sines involved in that case. You do get oscillation. When n is bigger than 2, it's more complicated. We don't go into details. How is all this related to diagonalization? We've got 6 minutes left. Say we're in the real case. Let's keep it to the real case here. At the moment, we're not going to have time for the complex case with diagonalization at the moment. Real case, and let's say distinct real eigenvalues, so that we have n linearly independent eigenvectors, which form a basis for our n, and this is your general solution. You form the matrix P, your change of coordinates matrix, to have columns that are those n linearly independent eigenvectors. Since those eigenvectors are linearly independent, and there's n of them, they form a basis for our n. This will be an invertible square matrix. P inverse will exist. Just saying that without writing it. We're in the case where these are linearly independent eigenvectors. The invertible matrix theorem guarantees this will be an invertible matrix. P inverse will exist. And if you form the matrix leave a little space here. P inverse AP, it will be a diagonal matrix, call it D, with the eigenvalues on the main diagonal. And zeros elsewhere. And that's good. We like diagonal matrices because they correspond to linear systems that are completely decoupled. You can easily find the general solution. You can easily solve a generic initial value problem. You can easily compute the matrix exponential. D and A are similar matrices here. When this kind of relation holds, they have the same eigenvalues. They have the same determined, same trace. That even holds in higher dimensions. This equation is equivalent to the equation A equals PD P inverse. It's also nice if A happens to be symmetric, as we've been talking about recently, then P can be taken to be an orthogonal matrix. To technically make it orthogonal, you also have to normalize the columns. You have to make them have unit length. And when you do that, its inverse is its transpose, and that's great because it just makes things so much easier. So symmetric matrices are very nice. They're orthogonally diagonalizable. P inverse equals P transpose makes computations a lot easier, even though they still involve square roots sometimes. To finish, what's the relationship between this stuff and the matrix exponential and solutions of generic initial value problems? Here's your generic IVP. For the original system with the original matrix, dy dt equals ay, y of 0 equals y sub 0, arbitrary but fixed initial condition. Again, this is my name. What I call the beautiful generalization is that the unique solution of this generic initial value problem is the matrix exponential e to the ta times y0. Give that a function a name, call it, say, capital phi, sub y0 of t. It's this. That's what's guaranteed by the beautiful generalization. You could say, in this context, the whole purpose of the diagonalization stuff, the Jordan canonical form stuff, and also what we have to do with real normal form in the complex case, is so that you can compute e to the ta more easily. That's the entire purpose. Or in the discrete case, compute a to the n power more easily. That's the entire purpose in the discrete case. Why? Because the corresponding generic IVP for the change of variable system, where you've got a new variable, call it vector u. The matrix is D. U of 0 equals U sub 0. It's, once again, by the beautiful generalization, its unique solution, give the function a different name like psi, but no quantum mechanics here, sub U0 of t is also e to the td times U0. E to the td, when d is diagonal, this is easy to determine. Easy to determine. When d is diagonal, e to the td is just e to the lambda 1t, e to the lambda 2t, etc. along the main diagonal, and zeros elsewhere. It's a diagonal matrix. If it's not diagonalizable, if d is like a real normal form, it's still relatively easy to determine. If it's a Jordan canonical form, it's still relatively easy to determine. That's the whole point. Final conclusion is, in 30 seconds, you want to relate these two things. You can compute e to the ta using the matrix P. And the relationship is similar to this relationship here. It's P e to the td, P inverse. These are similar kinds of relationships going on here. So e to the TD is relatively easy to compute. You know the matrix P. Hopefully you've computed its inverse. You can compute this to compute e to the TA. So the whole point is to help you solve this more easily, to compute the matrix exponential, even without Mathematica. Okay. All right. Have a good day.